Welcome back. Let's take a look at the issues we've found so far. We've found that the architecture program name is inconsistent. Our salary data is not in a numeric data type. And our salary column has some values that are marked as a dash. These are the three major problems that we will need to solve before we can run a regression analysis. Let's start with the first. Our academic program has an inconsistent name. Now, we as human beings can infer that ARCH probably refers to architecture. We know these are equivalent. However, if we ran a regression right now and we decided to use the program column as, say, a dummy variable or a categorical variable, well, we'd have two different categories for architecture, and that could throw off our results. So we need to make this consistent. Our academic program name needs to be made consistent. How will we do this? Well, some pseudocode is that for each entry in our program column that has the string value ARCH, we want to replace ARCH with the full word architecture. Here's our general data cleaning strategy. Throughout this course, when we clean a column of data, we're going to use the following strategy. We're going to take a copy of our column and put it in a new variable, do all of our cleaning on this extracted column, and then put the column back into our data frame. Optionally, at the very end of all of our cleaning, we'll save our cleaned data frame to a new CSV file. This is the strategy that we'll be using for the entire course. So how can we replace ARCH with the full word architecture? Well, we'll take advantage of the data frame column value replacement function, conveniently called replace. This function takes two parameters: the pattern that we're searching for and what value we want to replace the pattern with. So the pattern will be the text that we want to replace, and the replacement will be what we want to replace that text with. Here's our strategy in action. First, we create a new column. Let's call it program call. And we set it equal to salary-data.program. This gives us a copy of our data frame column. Next, we set our program call equal to the result of program call.replace, where we do our replacement of ARCH with the full word architecture. Finally, we put this clean column back into our data frame by saying salary-data.program equals our cleaned column. Let's give this a try in Python. I'll come back over to Spyder, and I'll create a new variable called program call. And I will set this equal to salary-data.program. If I run this code right now, you'll see that I have a new variable called program call, and it has a copy of all of the academic programs. I can do whatever I want to this column, and it will not affect the original data frame until I put this column back into the data frame. Watch. Let's clean the column. I'll say program call equals program call dot replace, and we're going to replace the string or text ARCH with the text ARCHITECTURE, architecture. And I'll run just this. Let's take a look at program call. Program call has first 6 entries are applied health sciences. And now look at this. ARCH has been replaced with architecture. Let's confirm to ourselves that we haven't affected the underlying data frame yet. So if we look, starting at row 6, index 6, ARCH is still present in our original data frame. We haven't updated the original data frame yet. But our column is now clean. Let's put this column back into our data frame. All we need to do is say salary data dot program equals program call. Now, if we open up the salary data frame, check it out. We have architecture all the way down. We have successfully cleaned the program column. This is the strategy we will use to clean columns throughout this entire course. Extract the column, clean the column, put the cleaned column back into the data frame. We've now solved the first out of our 3 problems, our architecture name being inconsistent. Next, we're going to deal with the salary column having some values marked as a dash and converting that salary column into a numeric data type. In order to do so, we need to talk about sentinel values. As you've noticed, our salary column has entries where the salary is a dash character. This is known as a sentinel. And sentinel values are text values that show up in number columns, and they're used to mark the presence of a special value. For example, they can be used to mark missing data, i.e., we don't know what the value of the average salary is for a student in a certain term. We may use sentinel values to indicate that we have low quality data. We may use sentinel values to indicate that we have censored data. For example, if we're reporting crime data and we don't want to individually identify anyone in particular, we can use a sentinel to say there were crimes committed, but there weren't enough to aggregate. In our case, we're going to use dash as a sentinel to indicate missing data. What do sentinel values look like? So a few common types are values that are outside the range of a column's valid values. For example, a salary of -1. Another giveaway for sentinels is very large or very small values. So you may see values in the millions or billions or negative millions or negative billions. A common one is, from my professional practice, has been in temperature reporting when we see, say, a temperature of close to 10,000 degrees Celsius when we're expecting the temperature to be somewhere between -50 and 50 degrees. Other sentinel values are string or text data such as an NA, NaN, null, dash, X, a blank. Sometimes 0 is used as a sentinel value. This is where data dictionaries can come in handy. So let's return to our salary column. When Pandas tries to read a CSV, if it runs into a value that it can't turn into a number, Pandas will store those values as strings, as text data. So in order to clean this column, we need to turn our values, this entire column, into numbers. How can we do this? Thankfully, Pandas has a built-in function called toNumeric. We pass the toNumeric function a column, and Pandas will try to convert that column into floating point or decimal numbers. How do we do this? First, we extract a copy of our salary column. Then we use pd.toNumeric and try to convert that column into number values. Let's give it a try. We'll come back into Python, and I'll get a copy of my salary column. by saying salary call equals salary data dot salary. I now have a copy of my salary column. Let's try converting these values into numbers. I'm going to say salary call equals pd.to_numeric. And inside the brackets, I'm going to provide my salary column. Let's run this code. This should convert our string data into numbers. But it did not. We got a value error. Unable to parse string dash at position 5. Well, what's going on here? Well, pandas can't convert our column into number values because of the dash character. Dash is not a number. So then how do we clean this column? Well, thankfully, we can tell pandas how to deal with this value that it can't convert via a parameter called errors. By default, we raise an error. In other words, if pandas can't convert the value into a number, it stops and throws an error in our face. Another option is to ignore, which doesn't have any effect. It doesn't help us. What we want to do is use coerce. This will turn any values that cannot be converted into numbers into the special value NaN. NaN represents not a number. This will be treated in our regression analysis as a missing row. So we will use errors equals coerce. Let's return to Python. We'll modify our toNumeric call by putting a comma after the salary call, and then we'll say errors equals coerce. If we run this now, notice how we didn't get an error this time. And if we look at our salary column, notice now how our salary column is highlighted. We're now dealing with numbers. But our salary data frame is not yet affected. Why? Well, we haven't put the salary column back into our original data frame, have we? Let's do that. Salary data.salary equals salary call. And now if we look at our salary data frame, take a look. It's cleaned. In fact, we can run a new description on our salary data. I'm going to say description cleaned equals salary data.describe. I'm going to run this piece of code after I finish my cleaning. Let's take a look. So for term, I've got 54 rows. For salary, I've got 47 rows. Because remember, we have some NaNs, not a numbers. Our average salary across all programs, across all work terms, is $21 an hour with a standard deviation of 3.6. Our minimum salary is $15.90 an hour, and our max salary is $29.71 per hour. That's a pretty good work term. And with that, we've now cleaned our data. We're ready to run our regression analysis and test our null hypothesis. Is there any relationship between work term, work experience level, and your expected salary? Well, let's give that a try. We'll come back into Python and let's set up our regression analysis. Recall from week 2, we'll be using stats models. So make sure at the top of your file you're importing statsmodels.formula.api as SMF. That way we don't have to type out that awful long line of code every single time. And we'll create our salary model 1. We'll set this equal to smf.ols and provide our formula. We want to predict salary from work term. And our data is our salary data. Finally, outside the brackets, use .fit. Then we can print out salary model 1 .summary. Now, before you run this regression, ask yourself, do you think there's going to be a relationship? Do you think that there's a relationship between work experience and your expected salary? Try pausing the video now. Ask yourself that question. Then, after you've paused the video, try running this regression and then compare what you get versus we're about to cover. All right, had a chance to think about it? Let's run this. I'll expand my right-hand column to give myself a bit more room to work with. Let's take a look at our regression results. We have an adjusted R-squared of 0.451, which is not bad. But more important, let's take a look at P greater than T. Well, we're significant at the 5% level for sure. That's good news. Our intercept is 16.1649, and our term is 1.5317. So what does this tell us? Well, it tells us that there's a statistically significant relationship between work term level and expected salary. This P greater than T gives us the percent chance that term has no effect on our dependent variable, which is salary. In this case, our value is so small that it's being rounded to 0. This gives us strong evidence for rejecting the null hypothesis, doesn't it? We're significant at better than the 5% level. Just to give ourselves another data point, let's grab the correlation for our salary data. I'm going to do salary core and create a new variable called salary core, and I'll set this equal to salary data.core. And if we take a look, salary and term are correlated quite strongly, 0.68. So again, let's interpret the results. What does this mean? Well, if we write this into a regression formula, our intercept is 16.1649. And for each term that we increase, we expect our salary to go up by 1.5317 units. Recall, our P greater than T is less than 0.05, so our coefficients are significant at least the 5% level or better. This is sufficient evidence that we can reject our null hypothesis that work term level has no effect on your expected salary. We can accept our alternative hypothesis, which says that work experience has a positive impact on salary for co-op students. Let's see how predictive our model is. So our formula is 16.1649 plus 1.5317 times the term. So let's say we're a first work term student. So our formula will be 16.1649 plus 1.5317 times our work term level, which is 1, which suggests that we should see a salary of $17.69.66, or in other words, $17.70 per hour. Let's look at our underlying data and see how accurate that prediction might be. If we look at our salary data, Applied Health Sciences, a work term level 1, makes about $15.90 on average. Architecture is $19 on average. Arts is $17.59 on average. Engineering is $18 on average. Environment is $17 on average. Mathematics is $19. Actuarial science is $20. Science is $16. And pharmacy is $16. So one conclusion is that it depends on the program. Recall, Our adjusted R squared was only 0.451. So our model's predictive power leaves a bit to be desired. But it doesn't sound too off the mark. Remember, your adjusted R squared is going to tell you how accurate your predictions will be. Our p greater than t is going to tell us how significant our findings are. And in this case, they're quite significant. Perhaps the model's not as predictive as it could be, but we do have a relationship between work term and your expected salary.